It should be clear by now that when the reverse bias voltage across the collector junction increases, the effective base width decreases. This phenomena itself is referred as base width modulation, base narrowing effect, as well as early effect. This is actually an undesirable effect. Consider a BJT and focus particularly on collector junction and effective base width. For some voltage V1, we will have some base width, and for another voltage V2 which is greater than V1, we will have effective base width which will be smaller than effective base width of the previous case. From the last lecture, we also know current through base is inversely proportional to effective base width. Therefore, in second case of higher reverse bias voltage, the current through the base increases because of reduced effective base width. This increases not only the current, but it actually increases current gain parameters also. You may think that it is good to have larger common emitter current gain, but it is actually not the case. Consider a normal light bulb in your home. When the power supply voltage lowers, then the bulb becomes dim. And when the power supply voltage becomes larger than the normal supplied voltage, then also it is undesirable as it can actually fuse out the bulb. Similarly, we may want larger common emitter current gain at manufacturing stage, but when it is placed in integrated circuit where upon its operation thousand other components in IC also depend, then it becomes undesirable to have significant fluctuations in common emitter current gain for small variations in applied reverse bias voltage. That's why early effect is undesirable. We can also understand the early effect through output characteristics graph of common emitter configuration where early effect is more clearly visible compared to other characteristics graph. This is the general manner of representing characteristics graph which shows multiple plots at different values of input current, which is base current in our case. However, I will be needing only one plot to make you understand the effect of early effect. Now, we will divide the plot into two parts. Consider the second portion which represents the active region. In active region, you know collector current is equal to common emitter current gain into base current. Since base current is kept constant, therefore collector current should also come out constant. But as can be seen, this is not the case. Collector current varies because common emitter current gain is not constant, and this variation comes because of early effect. If the early effect was absent, then this curve would come out to be a straight line parallel to x-axis. Also, if we extend the active region plot linearly, then it will cut the x-axis at certain voltage. Even if we consider different plots at different values of input current, then also if we extend, they will all cut at the same voltage. This voltage is referred as early voltage. From the graph, we can define output conductance, which is equal to differential of collector current with respect to voltage across collector to emitter. From the graph, we can also write output conductance is equal to collector current divided by early voltage plus voltage across collector to emitter. Also, we know that output resistance is inverse of output conductance. Therefore, we have output resistance equal to early voltage plus voltage across collector to emitter divided by collector current. This output resistance is a very important parameter in analog electronics. You will be solving a lot of questions based on hybrid pi model, and in that model, output resistance is included. Now suppose an extreme case has occurred when whole of the base width is depleted. You can recall in practical transistors, base concentration is small compared to collector concentration. Therefore, depletion region will extend to base region more fastly. This case is extremely undesirable and is referred as punch-through breakdown or reach-through breakdown. This is the dominant breakdown mechanism in BJT which destroys the performance of BJT permanently. Consider the shown diagram where base is completely depleted of charge carriers, giving effective base width equal to 0. From the unit of PN junction, we have the formula for part of the depletion width extending to the n-type region equal to we are trying to find the voltage corresponding to punch-through breakdown. Therefore, we will replace few symbols like reverse bias voltage will be replaced with reverse bias voltage corresponding to punch-through breakdown. Similarly, we know that Na represents acceptor impurity, and here in our case p-type is the collector. Therefore, acceptor impurity concentration will be replaced by collector doping concentration. Similarly, donor type concentration will be replaced by base doping concentration. So, for the BJT, the above formula will change to now if we square on both sides, we will get therefore, if we are supposed to find reverse bias voltage which will lead to punch through breakdown, we have the formula this is the exact formula by which we can find the reverse bias voltage at punch through breakdown. Also, you know that base is completely depleted. Therefore, part of depletion region extending to the n-type region can be replaced by base width. Remember that base width and effective base width are different parameters. As you are aware, in this subject, there are so many approximations. And here also, we have few approximations like reverse bias voltage corresponding to punch through breakdown is significantly greater than built-in potential. Therefore, while adding these two terms, we can ignore the built-in potential. Similarly, we know collector concentration is significantly greater than base concentration. Therefore, while adding these two terms, we can ignore the base doping concentration. Therefore, the above formula for reverse bias voltage at punch through breakdown will modify to. You may find this formula directly in books, and sometimes it confuses the students how and from where this formula came into existence. However, in competitive exams like GATE, students should try to use the exact formulas as much as possible. These exact formulas has another advantage. The thing is, it is quite easy if you understand the derivation to remember the formula, and even if you don't remember the formula, you can derive it in the exams if the time permits. However, if you keep learning the formulas without having any idea how and from where this formula came, then eventually there are chances that you may forget few formulas in the exam. So it will be better for you to remember the exact formula as well as the formula which came after approximations.